Thank you very much. So thanks everyone to come. Let me it's my great pleasure to present our speaker, Professor Ferenc Weisz, and the title High-Dimensional Summability in Lebesgue Points. And please, Professor Ferenc, go ahead. Please, thank you very much.
Thank you. It is a pleasure for me to give this talk. I will speak about summability of higher dimensional functions or Fourier transforms, about different types of Lebesgue points, and about different generalizations of the one-dimensional well-known Lebesgue theorem. Please, if you have questions, then ask me. First, I introduce some function spaces I will use later. I define the LP spaces in the usual way with the integral of the p power of the absolute value of f. If p is finite, then the infinity norm is basically the supremum norm. All results hold also for higher dimensional functions. For simplicity, I will present the results in the two-dimensional case. Probably you know the next definition. This is a generalization of the LP spaces. We say that a function f, measurable function f, is in the Wiener amalgam space W, LP, LQ, if this sum is finite. Here we take the LP norm over the unit square of the translates of f. Then this is a sequence, and here you can see the small LQ norm of this sequence. If q is equal to infinity, then we take the supremum, as usual. It is easy to see that if p is equal to q, so the two indices are the same, then we get back the usual LP spaces. The smallest such space is the W L infinity L1 space. This is contained in all LP spaces, and the LP spaces are contained in the largest such space in the space W L1 L infinity. The smaller space W L infinity L1 is widely used in the theory of Gabor analysis. We often take the window functions from this Wiener amalgam space. First, let us see the one-dimensional theorems, and I will generalize these theorems for higher dimensions, or in this talk for two-dimensional functions. So for a one-dimensional integrable function f, this is the definition of the Fourier transform, the usual definition. This can be extended for functions from LP, p is between 1 and 2. This is the usual theory. Here you can see the Fourier inversion theorem. In other words, the inverse Fourier transform of the Fourier transform of f gives back the original function f. If the function f is in the LP space and the Fourier transform of f is integrable. So this is a very nice formula, but the problem is that this condition, that f hat is an integrable function, is a very strong condition. If this is not true, then we can introduce the Dirichlet integrals St of f, and here we integrate from minus t to t. In this case, this integral does exist. We can use the Hausdorff-Young inequality, and then we can see that this integral is well defined. One of the deepest results of harmonic analysis is Carleson's result, or the result of Carleson and Hunt. If f is in the LP space, p is greater than 1, then the Dirichlet integrals STF converge to F almost everywhere. Okay, this is not true for p equal to 1. Then we don't have convergence. It is proved by Kolmogorov. It was proved by Kolmogorov. So if we want to extend this result for p equal to 1, then we have to consider a summability method. This means that here in the inversion formula, we will multiply by a function theta. I show this on the next slide. More exactly, we multiply by theta of S absolute value over T. T is a positive real number. These expressions are called theta means. The most known summability method is the Fejér method. Then theta is this triangle function. Theta S is equal to the maximum of 1 minus S absolute value and 0. This means that here I write, instead of theta, I write the definition of this. I use this function, and then we have to integrate only from minus t to t. We can also write this integral in the next form. Here we take the arithmetic mean or the integral mean of the Dirichlet integrals STF. So this is the most known summability method. Good. Now I introduce the Dirichlet maximal function. I define it by the subterm of overall h greater than 0. I integrate over the interval minus h, and I divide by 2h. So there are several definitions for this Dirichlet maximal function. For simplicity, I introduce this one. I think everybody knows that this maximal function is bounded on the p spaces. P is greater than 1. So the p norm of MF can be estimated by the p norm of F. P is greater than 1. But this is not true for p equal to 1. Then we can take a small norm of MF, not the one norm, the small norm, the so-called weak L1 norm. So this is smaller than the L1 norm of MF, and this small norm can already be estimated by the one norm of F. Using this inequality and the usual density method, we can show the next convergence result. The limit as h tends to infinity, so the limit of this integral is almost everywhere equal to f. We can also say that the derivative of the integral of f is almost everywhere f. This theorem is also due to Lebesgue. Here we can take f of x to the other side. Then the limit is also, this limit is also equal to 0 almost everywhere. Or the same, we write here the absolute value. This is the same. But if we go with the absolute value, if we go inside, then we get a larger result, a larger expression. It is not sure that this larger expression converges to 0. It is not sure, and this motivates the definition of the Lebesgue points. We say that a point x is a Lebesgue point of an integrable function f if this limit is equal to 0. Here you can see I have taken the absolute value inside. So it is not true from this result, it doesn't follow that this limit is equal to 0. But it holds almost everywhere. This is the next theorem. Almost every point x is a Lebesgue point of an integrable function. So this limit is equal to 0 for almost every x, but not for the same axis as in the previous case. Lebesgue proved the next result. If f is an integrable function and x is a Lebesgue point, then the Fejér means converge to f. So this is a very nice theorem because the definition of the Lebesgue points depends only on f. It is independent of the Fejér means or the Fourier transform of f. It depends only on f. So these are the one-dimensional theorems. In this talk, I will generalize this theorem. I will generalize this theorem for higher dimensional functions, for larger function spaces, not only for the Fejér means, but for general summability means, for the theta means. And yes, we will need, so I will consider 5 different summability methods. To this, I have to introduce 5 different concepts of Lebesgue points, 5 different maximal functions. Okay, so I start. In the two-dimensional case, the Fourier transform of an integrable function can be defined in the same way or a very similar way. Here is the definition. The Fourier inversion formula holds again if f is in the LP space, p is greater than 1 and smaller than 2, and f hat, the Fourier transform of f is integrable. So these theorems are the same as in the one-dimensional case, so very similar. If f hat is not an integrable function, then we can take again a summability method. We multiply here in the inversion formula, so we multiply by a function theta. More exactly, basically there are 2 different summability methods. In the first summability method, theta is a one-dimensional function, and we consider theta at the points the q norm of the vector st divided by capital T. So here we take the q norm of the vector st. Capital T is a positive real number. I denote this by sigma t q theta. Of course, I will have some conditions on theta, of course. In the literature and also in this talk, I will consider, we consider the subcases q is equal to 1, 2, or infinity. If q is equal to 1, then the summability is called triangular summability. For q equal to 2, it is called circular summability. And for q infinity, it is called cubic summability. In the other type of summability methods, we use 2 theta functions. Both are one-dimensional functions, and we consider the first function, theta 1 function, at the point s absolutely over t1, and the second function theta 2 at the point t over absolute value of t over the. Can you hear me?
Yes. Yes.
Now we can hear you.
Okay. So we multiply by these 2 theta functions. I will consider 2 subcases of this summability, so we have 5 summability methods. This second summability is called rectangular summability. For simplicity, I suppose that the theta functions, all theta functions are equal to 1 at the point 0. As special cases, we will obtain results for the Fejér summability method, for the Ries, Weierstrass, Aber, Picard, or Bessel summations. So all well-known summability methods are contained in this theta summation. Good, then I continue. First, I start with the case q equal to 2, so with the circular summability. Then I continue with the rectangular summability, with the two subcases of the rectangular summability, and finally I continue with the case q equal to infinity and q equal to 1. For each summability method, I have to use other Lebesgue points, different Lebesgue points, different maximal functions. Let us see the first case, the circular summability. Here q is equal to 2, and we take here the 2 norm of the vector of s and t. I introduce another function, theta 0 of st, so theta 0 is a two-dimensional function. This is equal to theta at the point st, the two norm of the vector s and t. This theta 0 is a radial function. And I suppose that theta 0 and the Fourier transform of theta 0 are integrable functions. We need this definition. So if this condition holds, then the integrals are well defined. The one or two-dimensional balls are denoted by BCH. The center of this ball is C, and the radius of the ball is H. Taking the difference of two balls with radius 2 to the power k and 2 to the power k minus 1 with the center 0. So this difference is denoted by qk, and this is defined dyadic corona. It is called dyadic corona. Q0 is the ball B0, 1. So the center is 0 and the radius is 1. I introduced the Hertz spaces. Measurable function f is in the Hertz space EQ. I need this definition also in the one and also in the two-dimensional case. This is why we have here D. So f is in the EQ space, in the Hertz space, if this sum is finite. Here we take the Q norm of f over the dyadic corona. Qk was the difference of two balls, and then we multiply by this power and take the sum. The measure of qk is approximately 2 to the power dk, and then we multiply it here by 1 minus 1 over q. If q is equal to 1, then this is 1 minus 1 over q is 0, so this is 1. We get the sum of the one norm of f over the dyadic corona, so this is exactly the L1 norm. So this is not so interesting. If q is equal to infinity, then this expression is equal to 2 to the power dk. So this is the measure of the set qk. This is the smallest space. If q is increasing, then the spaces are decreasing. Good. I introduced the Hardy-Littlewood maximal function for two-dimensional functions by this formula. This is very similar to the one-dimensional case. Here we integrate over cubes. You can see it, and we divide by the measure of the cube. And I defined it for, I used the p norm in the definition. In the one-dimensional case, I defined this operator only for p equal to 1. But here I will use it for greater p, also for greater p. We get the same theorem as in the one-dimensional case, or a similar theorem. Suppose that p is greater than or equal to 1 and smaller than infinity. Then this operator MP is bounded on the LR space. R is greater than P. Again, in the one-dimensional case, P was equal to 1. Good, and this operator MP is not bounded on the LP space. But the weak LP norm of MP, F, so the weak LP norm can be estimated by the P norm of F. Any questions?
No, I guess it's okay. We usually have questions at the end of the lecture.
Oh, okay. Then I continue. So this is well known. This theorem is well known. Well, these inequalities are well known. But we can also generalize these theorems for the Wiener amalgam spaces. First, the WLR L infinity norm of MPF can be estimated by the same norm of F. R is again greater than P, similarly to this case. If R is equal to P, then this is not true. Then we take again a weak norm, the so-called weak LP L infinity norm. You can see that with this supremum we take the weak LP norm over a unit cube, and then the supremum overall case. So this is the weak LP L infinity norm, or this the corresponding Wiener amalgam space. And this weak norm can already be estimated by the LP L infinity norm of F. The largest space on the right-hand side is the space WL1 L infinity, so if p equal to 1. Using this theorem for p equal to 1, we get the next convergence result. If F is in this larger space, WL1 L infinity, then the limit of this expression is equal to f of xy for almost every xy. We can take f of xy again to the other side, and we arrive at this formula. This motivates again the definition of the Lebesgue points. We take the absolute value inside and the p norm of this expression, and say that a point xy is a p Lebesgue point if the limit as h tends to infinity, so if the limit of this expression is equal to 0. It is again very similar to the one-dimensional case, but there we had p equal to 1. Only the 1 Lebesgue points were considered. All r Lebesgue points are also p Lebesgue points if p is smaller than r. So these are contained in each other. The sets are contained. We can prove the next result more exactly, that almost every point are p Lebesgue points. More exactly, almost every point xy is a p-Lebesgue point of f if f is in the space LP, Wiener-Ramagen space LP L infinity. This space WLP L infinity is much larger than the space LP. P is greater than or equal to 1 and smaller than infinity. Suppose that theta 0 is an integrable function. Theta 0 was the radial function in the definition of the theta means. So we suppose that theta 0 is integrable. P is greater than or equal to 1. 1 over P plus 1 over Q is equal to 1. Q is the dual index to P. If the Fourier transform of theta 0 is in the Hertz space EQ, then the theta means sigma t theta 2 theta, so that the theta means converge to f for all p-Lebesgue points of f when f is in the Wiener-Ramagen space LP L infinity. So we have the same space here as before, as in the previous theorem. This theorem was proved by Steiner and Weisz. This is not me. For integrable functions, so for L1 spaces, first space, and for the Ries means, without using the Hertz spaces. Later, with Professor Fejér, we proved this form of the theorem. The converse of this theorem holds also. More exactly, first we suppose that theta 0 and also the Fourier transform of theta 0 are integrable functions. P is the same as before, greater than or equal to 1, smaller than infinity, and Q is again the dual index to P. If we know the convergence for all p-Lebesgue points of f is in the LP space, then the Fourier transform of theta is in the Hertz space EQ. So you can see that the Hertz space is the optimal space in these theorems. Here I have written only the LP spaces, or the LP space, but the LP space is smaller, much smaller than the space W LP L infinity. So of course it holds also if I write here the larger space W LP L infinity. Okay, this is the generalization of the first generalization of the one-dimensional Lebesgue theorem, and of course this convergence holds almost everywhere, because almost every point is a p-Lebesgue point. This was the first generalization. Let's turn to the second one. As I said before, the second generalization is for the rectangular summability. Here is the definition of the theta means. In this definition, we use two theta functions, theta 1 and theta 2. We suppose again that all theta functions and the Fourier transforms are integrable functions. T is equal to the vector T1 and T2. I am very sorry, but I need some additional function spaces. This was the definition of the norm of the space WLPL infinity. We take the LP norm over cubes, over unit cubes, and then the supremum of these numbers. If we go inside with one supremum, then we get a larger norm, and of course a small space. So a function f is in the iterated Wiener-Ramagen space LP L infinity. If this expression is finite, you can see that I go back, I go inside with one supremum. If we change the p power of f by f to the power p plus log plus f times log plus f, then we get the space, the iterated space wi lp log l l infinity. So I have many function spaces. I'm sorry, it could be strange. Okay, but I continue. Log plus denotes the maximum of the logarithmic function and 0. The definition of LP log L is well known, I think. F is in the set LP log L if this integral is finite. So the integral of f to the power p times log plus f. So here this is the same as in the definition before. Here I integrate over unit intervals and take the subprimum in this order. The space LP L infinity is larger than the iterated space LP log L L infinity. This is larger than the LP log L space and larger than the C0 space. This is the space of continuous functions with vanishing at infinity. And the LP log L space is larger than the LR space. R is greater than P, and P is greater than or equal to 1. Now I can continue with the Littlewood maximal operator. This was the definition of NP, and it was investigated in the previous section. We integrate here over cubes and divide by the measure of the cubes. I modify now this definition, and I integrate over rectangles. I divide by the measure of the rectangles. This maximal operator is called strong Littlewood maximal operator. The original maximal operator MP is bounded on the LR spaces, as probably you remember. R is greater than P. It is not true for R equal to P, but then MP is of weak type PP. This is not true for the new maximal operator. So the strong maximal operator is bounded on the LR space, R is greater than P, but the weak type PP inequality does not hold. The problem is that the measure of the rectangle can be small, even if one side of the rectangle is small and the other side is large. So the product can be small in this case, also in this case. So this is the reason why the weak type PP inequality does not hold. But let us see the next theorem. So P is greater than or equal to 1. If R is greater than P, then the strong maximal operator is bounded on the LR space, as I said before. It is not true for R equal to P, and the weak type inequality is not true, so this weak LP norm of MSP F cannot be estimated by the P norm of F, but it can be estimated with this right-hand side, so by the LP log L norm plus a constant. On the left-hand side, I have to suppose that X is in a compact interval or compact set. Okay, this was no. But we can also generalize these inequalities for the Wiener amalgam spaces. And here I have to use the iterated spaces, iterated Wiener amalgam spaces. So this was the reason that I introduced the iterated spaces. First, the WLR L infinity norm of MSPF can be estimated by the iterated norm LR L infinity of F. If I omit the iterated, if I write here also only the R L infinity norm, so the same norm as here, then the theorem is not true. I have to choose here a larger norm, and this is a larger norm than the WLRL infinity norm. We have also a weak type result. We take on the left-hand side the weak LP-L infinity norm, as before for the operator NP. And this can be estimated on the right-hand side by the iterated LP log L infinity norm of F plus constant. The largest space on the right-hand side is the L1 log L infinity norm, and we can prove easily the next convergence result. So if F is in the iterated space L1 log L infinity in the larger space, then the limit, this limit is equal to F almost everywhere. Here we integrate again over rectangles and divide by the measure of the rectangle. Yes. A point xy is called a strong Lebesgue point if this limit is equal to 0. H tends to 0 means that both coordinates h1 and h2 tend to 0. Here you can see again the definition of the Lebesgue point. So here we integrate over cubes, and here in the new definition we integrate over rectangles. Almost every point is a strong Lebesgue point. If F is in the iterated space LP log L infinity, P is greater than or equal to 1. If the functions theta I are integrable functions, P is greater than or equal to 1, Q is the dual index, and if the Fourier transform of theta I is in the head space EQ, then that means the sigma t theta means converge to F for all strong Lebesgue points. F is in the iterated space LP log L infinity. If we choose here a larger space, say the LP space, a larger space WLP L infinity, then the theorem is not true. The theorem is not true. The same. I can say the same from this theorem. The theorem is not true for even for the LP spaces. T tends to infinity means that both coordinates T1 and T2 tends to infinity. The iterated space LP log L infinity is larger than the LP log L space or the space C0 or LR. This was the second generalization. In the third generalization, I consider again the rectangular summability, but I suppose that the vector T is on the diagonal or in a cube. So the definition is the same. I suppose that the difference is only that I suppose that T is in a cone. This case was considered first by Hardy, no, not Hardy, Littlewood, but by Marcinkiewicz and Zygmunt. I introduce a new head space, the so-called the weighted head space. The definition is almost the same as before. The only difference is that here I have a positive number omega. So this is the weight. I need only the definition in the one-dimensional case. Qk is the same. If omega is equal to 0, then we get the same head space. Again, if Q is increasing, then the spaces are decreasing. The smaller space is E infinity omega. This was the definition of the strong maximal function. We integrate here over rectangles. I modify again this definition. and introduce the MP omega maximal operator. I integrate here again over rectangles. I'm divide here by the measure of the rectangles, but I have also this weight function. Omega is a positive function, and I multiply by this weight, and then I take the supremum. Here we get the same result as for the maximal, same results as for the maximal operator MP. So the weak type results holds also, the original weak type results holds also. The result are different from the result corresponding to the strong irreducible maximal function. This is because of this weight. Here is the theorem. So this MP omega maximal operator is bounded on the LR space. The weak LP R is greater than P. The weak LP norm can be estimated by the LP norm of F. And here are the generalizations for the Wiener-American spaces. Probably I go ahead because these inequalities are the same as before for the operator MP. Here omega is missing. This was the definition of the P-Lebesgue points, and this the definition of the strong P-Lebesgue points. We can write the second definition in the next form. We take first the supremum overall H1 smaller than R, H2 smaller than R, and then the limit R goes to 0. Using this form, we can introduce a new Lebesgue point, the P omega Lebesgue points, the concept of the P omega Lebesgue points. Here we integrate again our rectangles. We multiply by the same weight as before in the definition of the maximal operator. We take the supremum for all rectangles with sides smaller than R, and then R goes to 0. So this is the definition of P omega Lebesgue points. And we have the same results. Almost every point is a P omega Lebesgue point. If F is in the Wiener-American space, WLPL infinity, P is greater than or equal to 1, omega is always a positive number. If theta I is an integrable function, P is greater than or equal to 1, Q is again the dual index, and omega is greater than 0, and the Fourier transform of theta I are in the weighted head spaces. Then the theta means converge to F for all P omega Lebesgue points. F is again in the space LPL infinity. Here you can see that T goes to infinity, but T is in the con. The first result in this direction was proved by Marcinkiewicz and Zygmunt. They proved the almost everywhere convergence of the Fejér means of Fourier transforms. So without head spaces, without Lebesgue points, only that the Fejér means, the two-dimensional Fejér means, converge to the original function, almost everywhere to the original function F. This was the third generalization. Let us turn to the fourth generalization, to the cubic summability. Then Q is equal to infinity. So this is the infinity norm of the vector ST. Instead of the hash spaces, here I use another concept. I suppose that theta is a differentiable function. And moreover, I suppose for 3 or 4 technical conditions. Here alpha is a positive real number. I will use it later. This was the definition of the P omega Lebesgue points. If in addition this limit is also equal to 0, then we say that xy is a strong p omega Lebesgue point. What is the difference? The difference is that here we integrate over a rhombus, not over rectangles, over a rhombus or over a parallelogram. It is over a parallelogram. I divide again with the measure of the parallelogram. So I need additionally this definition of this limit. Almost every point is a strong p-Lebesgue point. If f is from the finite amalgam space L, P, L infinity, p is greater than or equal to 1. If p is greater than 1, then in this theorem I don't use this second condition. I use also the first condition, so the p omega Lebesgue points. If p is greater than 1, let us see the theorem. P is greater than 1, and omega is small enough. I need also this condition. Omega is small enough. If f is in the LP, L infinity space, then the theta means, the cubic theta means converge to f for all p omega Lebesgue points of f. This theorem is not true for p equal to 1. If p is equal to 1, then I have to use also the second condition, so I can state a theorem for strong 1 omega Lebesgue point. So Lebesgue points. This is the next theorem. If f is p is equal to 1, then I have here at the L1, L infinity space, of course, the 1 omega Lebesgue points, but as I said, I need the strong 1 omega Lebesgue points. So f is in the space W, L1, L infinity, omega is small enough, then the theta means converge to f for all strong 1 omega Lebesgue points. The first result was proved by Marcinkiewicz. He proved that the almost everywhere convergence of the Fejér means for the L1 log L functions, and later Zizyarsvili proved it for the L1 space, but here I have to write t square, of course, two-dimensional functions. So later Zizyarsvili proved it for L1, and as you can see, I proved it for I proved it for Lebesgue points and for larger function spaces. This was the fourth generalization. In the fifth generalization is very short. Here Q is equal to 1. This is the 1 norm of SD, and here I get the same result. If f is in the space L1, L infinity, omega is small enough, then the triangular theta means converge f for all strong 1 omega Lebesgue points. Do I have some minutes? I can speak about in 2 or 3 slides about strong summability. Probably it was interesting.
Yes, of course, you still have time.
Thank you. The theta, the definition.
Around 10 minutes.
Okay. The definition of the theta means, so I will speak about strong summability of one-dimensional functions. And to prove these theorems, I used the previous theorems. The strong summability is again a hard topic of harmonic analysis, I think. So the theta means can also be written in this form. Here is the derivative of theta. Of course, I suppose that theta is differentiable, and here you can see the Dirichlet integral SDF. I proved before that the theta means converge to f for all 1 Lebesgue points. If f is in the space W, L1, L infinity, but here I have written L1, LQ, this is a small space, but the Dirichlet integral can be defined also only for these functions. It cannot be defined for the L1, L infinity space. So this is why I will write here in this section always this space. So, in other words, this integral tends to 0. And the question is, if I write here the absolute value inside the absolute value, where this integral converges to 0, almost everywhere, or at Lebesgue points. The short answer is yes and no. But more precisely, theta is usually a decreasing function. Then theta prime is negative. So it is enough to take the absolute value of the difference. I will do this. And I can write here instead of the absolute value to the power r. If this limit is equal to 0, then I say that f is strongly summable. So you can see here the first result. Suppose that f is in the L1, LQ space, q is greater than or equal to 1, and smaller than infinity, r is a positive real number. If x is a one Lebesgue point of f, and f is locally bounded at the point x, then f is strongly summable. If we leave this condition that f is locally bounded, then the theorem is not true. So it is not true that f is strongly summable for each one Lebesgue point. This was proved by Hardy and Littlewood. But if we take here, instead of the L1 norm, the LP norm, you can see it in the next theorem. So f is in WLPLQ, p is greater than 1, q is the same, and I is the same as before. And if x is a p Lebesgue point, then f is strongly summable at the point x. This was proved by Hardy and Littlewood for Fourier series and for Fejér means. As I said before, the theorem is not true for p equal to 1. But what is the case? Do we have any results for p equal to 1? Almost everywhere results. I said the convergence is not true for all Lebesgue points. So, okay, if x is a one Lebesgue point, then this integral, the limit of this integral is 0. This is almost the definition of the Lebesgue points. In the definition I used here the integral from minus h to h. But this is also true. Now I write, instead of h, I write I to the power t. I is an integer, t is a positive real number. Then this limit is also equal to 0. Okay, a point x is called a Gabisonia point. If for all gamma greater than 1, smaller than infinity, the sum of these expressions over all I, positive integers, so the sum of this expression to the power of gamma is equal to, the limit of this sum is equal to 0. So this could be very strange, but you can see again that this definition is depending only on f, not on the summability methods. Good. Every Gabisonia point is a one Lebesgue point. So the set of the Gabisonia points are smaller as the set of the one Lebesgue points. But almost every point is a Gabisonia point. If f is from the largest Wiener amalgam space L1, L infinity. If f is in the space L1, LQ, q is greater than 1, greater than or equal to 1, smaller than infinity, r is a positive real number, and x is a Gabisonia point of f, then f is strongly summable at the point x. This means, of course, that the convergence holds almost everywhere. Here you can see the same result for the Fejér means. Then we have to integrate only from 0 to t, and theta prime is then theta is the triangular function, and the derivative of theta prime on the right hand side, the derivative of theta is equal to -1. So this is the result for the Fejér means. This was proved by Gabisonia for the Fejér means and for Fourier series, and later I extended it for theta means and for these larger spaces. Of course, the space WL1LQ is larger than the LQ spaces. Q is between 1 and infinity, so we get this result also for all LQ spaces, for the L1 space and also for other LQ spaces. Q is greater than or equal to 1 and smaller than infinity. Basically, this is my last theorem. In addition, I can show you some quickly. I can show you some summations, some summability methods. Here you can see the definition of the Fejér summation. I showed you. I showed you before. The second example. This is the De La Vallée-Poussin summation. The Jackson De La Vallée-Poussin summation. The results holds also for these summability methods. These are special cases. This is the Rogozinski summation, the Weierstrass summation. Here theta is equal to e to the power minus t to the power gamma. If gamma is equal to 1, then this is the Abel summation. Here you can see the Picard and Bessel summation, and in the last one, the Ries summation. If delta is equal to gamma is equal to 1, then we get the Fejér summation. Of course, there are other summability methods which are special cases. So this is my last slide. Thank you very much.
Thank you, Professor Weisz, for very nice presentation. And now, okay, guys, we have questions. Are there any questions?
Yes, there is a question. The question is, do you see any applications of your results, for instance, in the sphere of image procession?
I don't know. This is my quick answer, short answer, I don't know.
Yeah, sometimes it's very general question about applications. Okay, more questions, maybe more related to the talk.
This is a theoretical topic, I think.
I have a remark anyhow.
Okay.
And, first, apologize, Alexey, for that I could not be on all seminars. The reason was that I have been traveling from Uppsala today. But the first I do when I come to the flat is to open this famous seminar.
Thank you.
Then I see my friend, Ferenc Weisz as speaker. And hello, Ferenc. And I really appreciate that, but I could only see half of the presentation. But since we write joint book, I know something about your impressive work also from before. So, but what I saw was very impressive, really. And also I have a general remark, I think, on behalf of all participants of this seminar to Alexey and the organizer. Really thank you on behalf of all participants. I am something like Nestor in this international team. So I really thank you for this, that we can participate such impressive international seminar. So thank you all of you.
Thank you, Lars. Thank you very much. Well,
may I give small comment?
Okay, please
Yes.
go ahead, Maria.
I want only to say that it was about 1990, about 30 years ago, I introduced and studied another generalization of Lebesgue points, two-dimensional Lebesgue points. It was and I think that Lebesgue points can be more or less this can be described also in that terms, but I did not study summability. I studied, for example, order of growth of square partial Fourier sums. But I guess there is some connection between this generalization of Lebesgue points and that ones.
Mm-hmm. Could you please send the paper or the...
Yes, there are some papers, probably in mathematical notes, and a couple of papers, yes, about 1990.
Maybe you send links. Maria, maybe you send links to this paper.
Send, yes, of course, I can send.
Okay. You can send directly, or you can send to us, and we can communicate to Weisz, to Professor Ferenc.
Okay.
Thank you.
Okay, but I understand this is kind of another subject close to this talk. Okay, so may I have one also general question? Well, you've been speaking very nice about this classical theory and generalization of this classical theory, but I wonder, are there any paper devoted to similar issues for functions in Orlich spaces? I mean, we know what happens if we take a function from Lebesgue space. Then what would we have if we take a function from Orlich space? I believe that if Young function is between some t to the power p, then it's kind of clear that the limit exists. But in general case, are there any work, maybe papers?
It is very interesting, but I didn't see such papers.
Okay, but maybe just kind
of a remark about this, Alexey. Really, yeah. I think it's too new, this new way to look at classical Fourier analysis. They have not still developed with different function spaces and so on. So it's a very, very great potential. So everything which is done in classical Fourier analysis, that it's a possibility to do some similar with other function spaces, Morris spaces it will come, I'm sure, because this theory will be also very strong, and we hope that this new book also shows this.
Yes. And can you speak a couple of words about your book so people will know about this?
Or maybe Weisz is best to say about it.
Okay. Just for a presentation of.
I can say some words. We write a book about relinking Fourier series. We proved the almost everywhere result, so the result of Carlson and the norm convergence also, and at the end we investigate also the Vilenkin Fourier series in Lebesgue spaces with variable exponents.
In also variable exponents, okay.
Yes, variable exponents if the LP spaces if P is a function.
Mm-hmm. Well, I understand when you take convergence pointwise that you're okay with writing P of X in the norm, you don't write 1 over P of X, right?
Yeah.
So that's the reason that you can do this for variable spaces.
But it's not so simple.
No, I understand. It's not, of course, it's not so simple, but I'm just imagining that you don't use much norms, so it can be done.
A new definition of the norm, so we cannot write 1 over P of X. We define it similarly as the Orlich norms are defined. So we have an infimum of lambda, so that the integral is more than 1, something like that.
Okay, very nice. Thank you. Are there any questions? I see one more question. Please go ahead.
Can also, Marcel, would you like to say something about the book?
Excuse me, I don't hear you.
Oh, sorry.
I guess we have one question, no?
Yes, hello.
I see. Okay, please go ahead. Yes.
Thank you very much. So my question is, as it is known, there is a certain connection between Gölder continuity of a function and Gölder estimates for convergence of the Lebesgue point integral. Have you considered these issues for your cases? I mean about the connection with the Gölder condition.
No, I didn't consider it. Yes.
I see. Thank you very much.
Okay,
but
guys,
that is
thank
a
you.
good question. It's a good question, and I think a lot of such questions will come, you know, when it.
Yes, it is a good question.
There's no new possibilities here when you compare with other classical cases.
Yes, it shows it's a very prosperous area of investigation. Okay, more questions, please. So if we don't have more questions, then please let us thank speaker for a very nice presentation.
Thank you very much. For me. Thank you.
Thank you very much. It was our very nice seminar, but it was like last seminar in this series of seminars. We will have a short break for August, and we will come back in September. But in August we have few conferences, some of them online, some of them offline. So I hope to see some people from this seminar also face to face. So thanks again to the speakers, thanks to everyone for coming to our seminar, and see you soon. Thank you.
Thank you. Goodbye.
Thank you. Bye-bye.
Thank you.
It was nice to see you.
Thank you very much. Goodbye.
Goodbye.
Thank you very much. Goodbye.
Thank you.
Bye-bye. Спасибо, до свидания.
Всего доброго.
Goodbye.
So Lars, thank you very much for your very nice words, very kind words as usual.